Hello, friend. Some nights the universe feels closer than it should. Stars hum with a frequency we can't quite hear. Darkness holds more weight than light. And somewhere in the vast nothing between galaxies, something is ending. Slowly, quietly, beautifully. The universe is dying. And maybe that's the most peaceful thing you'll hear tonight. We don't often think about endings. We're wired to cling to beginnings, to growth, to the bright promise of forever. But tonight we're going to drift towards something different. Tonight we're going to explore the end of everything, the final chapter of the cosmos, and discover why it might be the most beautiful story ever told. Before we begin though, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. The universe is roughly 13.8 billion years old. That's ancient beyond comprehension. Yet, cosmically speaking, it's still young, still warm, still glowing with the afterglow of its violent birth. But physicists have done the math, peered into the equations that govern space and time, and they've seen something we rarely talk about. They've seen the end. Not tomorrow, not in a million years, but eventually, inevitably, the universe will stop. It will grow cold, silent, still. And in that stillness, there's a strange kind of grace. Scientists suggest there are several ways the universe might end. Each one sounds catastrophic. The big freeze, the big rip, the heat death. But when you look closer, when you let the science settle into your bones, you realize something unexpected. These endings aren't violent. They're slow, gentle even, like falling asleep after the longest day you've ever lived. Right now, as you listen to this, the universe is expanding. It has been since the Big Bang, that first explosive breath that set everything in motion. But it's not just expanding, it's accelerating. Galaxies are drifting apart faster and faster, pulled by a mysterious force we call dark energy. It sounds ominous, but really it's just a name for something we don't yet understand. A whisper in the mathematics, a pull we can measure but not explain. In 1998, two teams of astronomers were studying distant supernovae, exploding stars so bright they can outshine entire galaxies for a few weeks. They expected to find that the universe's expansion was slowing down like a ball thrown into the air, eventually slowing before it falls. Instead, they found the opposite. The universe was speeding up, accelerating into the dark. It was like watching someone walk away from you, only to realize they're breaking into a run, and soon they'll be too far to call back. This discovery won them the Nobel Prize. It also forced us to confront a truth we'd been avoiding. The universe doesn't want to hold still. It doesn't want to collapse back into itself, to return to the singularity it came from. It wants to spread, to thin, to dissolve into the infinite. Dark energy makes up about 68% of the universe. That's more than matter, more than all the stars and planets and black holes combined. It's the dominant force shaping the future of everything, and yet we don't know what it is. Some researchers describe it as a property of space itself, an inherent tension woven into the fabric of reality. Others call it a field, something dynamic and evolving. But whatever it is, it's winning. It's pulling the cosmos apart, thread by thread. Here's what that means for the future. In about 150 billion years, every galaxy beyond our local group, the small cluster that includes the Milky Way, Andromeda, and a few dozen others, will have drifted so far away that their light will no longer reach us. The sky will go dark. Not because the stars have died, but because they've sailed past the edge of what we can see. Future civilizations, if they exist, will look up and see only their own galaxy. They'll have no evidence of the wider universe, no proof that anything exists beyond their cosmic neighborhood. Imagine that. A sky with no distant galaxies, no proof of the Big Bang, no evidence that the universe is expanding. Astronomers in that far future might study the heavens and conclude they live in a static, eternal cosmos. They'd be wrong, but they'd have no way of knowing. The universe would have hidden its own history. It's humbling, isn't it? We live in a moment when the universe is still young enough, still close enough for us to see its full story. We're lucky. Cosmically lucky. We exist in a window of time where the evidence of the Big Bang still lingers in the cosmic microwave background, where distant galaxies still shine in our telescopes, where we can piece together the past and predict the future. But that window is closing, slowly, inevitably. There's something poetic about this. The universe is not just expanding, it's forgetting, erasing its own history, letting the evidence of its birth fade into the dark. It's like an old photograph left in the sun, colors bleeding away until only the faintest outline remains. And one day, even that will vanish. Some people find this depressing. The idea that everything we know, everything we've built, everything we've discovered will one day be swallowed by an ever-expanding void. But there's another way to look at it. Endings give meaning to beginnings. Impermanence makes every moment precious. If the universe lasted forever unchanged, and unchanging would anything matter, would there be any reason to look up at the stars and feel wonder? The Japanese have a concept called mono no aware. It translates roughly to the pathos of things, or the beauty of impermanence. It's the bittersweet awareness that everything is fleeting. Cherry blossoms bloom for just a few weeks, and that's what makes them beautiful. A sunset lasts minutes, and that's what makes it worth watching. The universe will end, and maybe that's what makes it worth studying, worth marveling at, worth whispering about on quiet nights like this. Carl Sagan once said, "We are a way for the cosmos to know itself." Think about that for a moment. The universe is not some separate thing out there indifferent to us. We are made of it. Every atom in your body was forged in the heart of a star. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it came from stars that lived, burned, and died billions of years ago. You are stardust, literally. And that means when you look up at the night sky, you're not looking at something foreign, you're looking at home. And if we're part of the universe, then the universe is part of us. Its birth is our birth. Its story is our story, and its end, whenever it comes, is not an ending we should fear. It's just the final note of a song that's been playing since the beginning of time. Right now, the universe is still singing. Stars are still being born in the swirling chaos of nebulae. Galaxies are still colliding, merging, creating new structures in the dark. Black holes are still devouring matter. Neutron stars are still spinning at impossible speeds. And somewhere on a small blue planet orbiting an ordinary yellow star, people are still looking up and asking questions. But the tempo is slowing. The universe is cooling. The era of star formation, the age we live in now, where new suns ignite and light up the void, will not last forever. In a few trillion years, the last star will flicker out. The universe will enter what cosmologists call the degenerate era, a time when only the fading embers of dead stars remain. White dwarfs, brown dwarfs, cold, dim, slowly radiating away their last traces of heat. And yet, even that is not the end. Even after the stars go dark, the universe will continue. It will keep expanding, keep cooling, keep drifting toward a state of maximum entropy where no energy remains to do work, where no structure can form, where everything is spread so thin and so cold that nothing can happen, ever again. This is called the heat death of the universe. It sounds grim, final, but when you think about it, really think about it, it's just rest, deep eternal rest. The kind of rest that comes after a life well lived. After all the struggle and noise and chaos, the universe will finally be still. And maybe that's not something to mourn. Maybe that's something to honor, to respect, to see as the natural conclusion of a story that began with unimaginable violence and ends with unimaginable peace. Tonight we're going to walk through that story. We're going to visit the dying stars, the evaporating black holes, the silent voids between galaxies. We're going to see the 3 possible endings scientists have imagined. And we're going to ask the question that haunts every cosmologist who stares too long into the equations. What comes after? You don't need to understand everything. You don't need to remember the numbers or the names. Just rest and let curiosity do the listening. Let the universe tell you its final secret. That endings are not tragedies. They're transformations. And sometimes the most beautiful thing a story can do is know when to close. The universe has already begun its goodbye. It started billions of years ago, the moment dark energy tipped the balance and expansion became inevitable. And it will continue long after we're gone, long after our sun has burned out, long after our galaxy has merged with Andromeda and formed something new. But that doesn't mean it's over, not yet, not for a long, long time. So let's take our time. Let's wander through the twilight of the cosmos together. Let's see what the end looks like when you stop fearing it and start listening to it. Because the universe is dying, slowly, quietly, beautifully, and we're here to witness it. Let's drift deeper now into the signs that the universe is already slipping away. The universe doesn't announce its departure. There's no fanfare, no warning bell. It just starts drifting quietly, like someone slipping out of a room while you're not looking. And the strange thing is, we didn't notice for most of human history. We thought the cosmos was eternal, unchanging, a vast stage on which our little dramas played out. But in 1929, everything changed. Edwin Hubble, working at the Mount Wilson Observatory in California, pointed his telescope at distant galaxies and measured something unexpected. They were moving, all of them, away from us. And the farther away they were, the faster they were receding. It was as if the entire universe was exhaling, pushing everything outward, and we were caught in the breath. This wasn't just motion through space. This was space itself expanding, stretching like fabric pulled at the edges. And if space is expanding now, that means it was smaller in the past, much smaller. Keep rewinding far enough, and you arrive at a single point, a moment of infinite density and heat. The Big Bang, the beginning of everything. But beginnings always carry endings inside them. The moment the universe started expanding, its fate was sealed. The only question was how it would end. For decades, cosmologists debated 2 possibilities. Maybe the universe had enough matter to pull itself back together, through gravity collapsing into a big crunch. Or maybe it would expand forever, growing colder and emptier, fading into a big freeze. The answer depended on the total mass of the universe. Too much mass and gravity wins. Too little and expansion wins. In the 1990s, 2 teams of astronomers set out to settle the debate. They studied Type Ia supernovae, exploding white dwarf stars that always shine with the same brightness. Because their luminosity is predictable, they work like cosmic mile markers. By measuring how bright they appear versus how bright they should be, you can calculate their distance. And by measuring their redshift, how much their light has stretched toward the red end of the spectrum, you can determine how fast they're moving away. The researchers expected to find that the universe's expansion was slowing down. That gravity was putting the brakes on, even if just a little. Instead, they found the opposite. The expansion was accelerating, speeding up, as if something was pushing the universe apart from the inside. They called this force dark energy. Though the name doesn't explain much, it's not dark in the sense of being shadowy. It's dark because we can't see it, can't touch it, can't understand it. It doesn't interact with light or matter in any way we can detect. We only know it's there because of what it does. It pushes, relentlessly, quietly, and it's winning. Dark energy makes up roughly 68% of the universe. Dark matter, another mystery we can't see but can measure through its gravitational effects, makes up about 27%. That leaves just 5% for everything we can actually observe. Stars, planets, galaxies, gas clouds. All of it is a tiny minority in a cosmos dominated by forces we barely comprehend. Think about that for a moment. Everything we've ever seen, every photograph taken by the Hubble Space Telescope, every distant quasar and glowing nebula, it's all just the tip of the iceberg. The universe is mostly made of things we can't see, and the invisible part is pulling the visible part apart. Scientists suggest that dark energy might be a property of empty space itself, a kind of inherent tension woven into the vacuum. In quantum mechanics, even empty space isn't truly empty. It seethes with virtual particles popping in and out of existence, borrowing energy from the void, and paying it back so quickly we can't measure them directly. Maybe dark energy is the cumulative pressure of all those tiny fluctuations. Or maybe it's something else entirely, a field like the Higgs field permeating all of space. We don't know yet, but we can measure its effects with astonishing precision. Here's what those effects look like. Right now, the universe is expanding at about 70 kilometers per second per megaparsec. That's a strange unit, but here's what it means. For every 3.26 million light-years of distant space is stretching at a rate of 70 kilometers per second. So a galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. The farther you look, the faster things are moving. And because the expansion is accelerating, those speeds are increasing. In the distant future, billions of years from now, galaxies will be racing away from each other faster than the speed of light. Not because they're moving through space that fast, but because the space between them is growing. It's like standing on a conveyor belt that's speeding up. You're not running, but you're moving farther and farther away from where you started. This has profound consequences. There's a boundary in space called the cosmic event horizon. Beyond this horizon, objects are receding so fast that their light will never reach us no matter how long we wait. Right now, that horizon is about 16 billion light-years away. Anything beyond that is lost to us forever. Not because it stopped existing, but because the universe has grown too fast for its light to catch up. In 1 trillion years, almost all galaxies beyond our local group will have crossed this horizon. They'll still be out there, but we'll have no way of seeing them, no way of knowing they exist. Future astronomers will look at the sky and see only their own galaxy and its nearest neighbors. They'll have no evidence of the wider universe, no cosmic microwave background to study because it will have redshifted into invisibility. No distant supernovae to measure, no proof that the Big Bang ever happened. It's a strange kind of loneliness, not the loneliness of being the last person on Earth, but the loneliness of being the last civilization in a visible universe, surrounded by neighbors you can't see, can't reach, can't even prove are there. Some researchers call this the cosmic censorship of the future. The universe will hide its own history. It will erase the evidence of its birth, its expansion, its evolution. And any intelligent beings living in that far future will have to reconstruct cosmology from scratch with far fewer clues than we have now. But that's trillions of years away. Right now, we're in the golden age of cosmology. We have the cosmic microwave background, a faint glow of light left over from 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. We have distant galaxies to study, whose light has been traveling toward us for billions of years, showing us what the universe looked like when it was young. We have supernovae and gamma ray bursts and quasars, cosmic beacons scattered across space and time. We're lucky. Unbelievably lucky. We exist in a window of time when the universe is still legible, still willing to share its secrets. But that window is closing, slowly, steadily, inevitably. The Milky Way and Andromeda are on a collision course. In about 4 billion years, they'll merge, creating a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. It sounds violent, 2 galaxies smashing together, but it's actually a slow, graceful dance. Stars are so far apart that even during a galactic collision, almost none of them will actually hit each other. They'll just pass through like ghosts moving through ghosts, their orbits reshuffled by gravity. After the merger, Milky Way will be one of the last large galaxies in the observable universe. Most others will have drifted beyond the cosmic horizon. We'll be an island, a lonely city of stars in an ocean of expanding darkness. And we'll keep drifting. The space between Milky Way and the next nearest galaxy will stretch and stretch faster and faster until even light can't bridge the gap. The universe will become a collection of isolated island galaxies, each one cut off from all the others, each one alone. Does this feel sad to you? It does to some people. The idea of cosmic loneliness of galaxies drifting into permanent isolation feels like a tragedy. But there's another way to see it. Imagine you're standing on a beach at sunset, watching a ship sail toward the horizon. Eventually it disappears, not because it sank, but because the curve of the Earth hides it from view. It's still out there, still sailing, still moving through the water. You just can't see it anymore. That's what's happening to the universe. Galaxies aren't disappearing. They're just sailing past the edge of what we can see. And maybe that's not a loss. Maybe that's just the natural rhythm of a cosmos that's always been bigger than we could comprehend. The ancient Greeks thought the universe was a series of nested spheres, Earth at the center surrounded by the moon, the sun, the planets, and finally the fixed stars all rotating in perfect circles. It was a small, tidy cosmos, comfortable, comprehensible. Then we learned the Earth orbits the sun. Then we learned the sun is just one star among billions in the Milky Way. Then we learned the Milky Way is just one galaxy among trillions. And now we're learning that even those trillions of galaxies are just a fraction of what exists. Most of the universe is already beyond our reach, hidden behind the cosmic horizon. Every discovery makes the universe bigger, stranger, less knowable. And maybe that's the point. Maybe the universe isn't meant to be fully understood. Maybe it's meant to be wondered at, to humble us, to remind us that we're small, but we're part of something immense. Right now, at this very moment, a photon of light is leaving a distant galaxy, beginning a journey that will take billions of years. By the time it arrives, if it ever arrives, the galaxy it came from might have drifted so far that its light will never reach us again. That photon might be the last messenger, the last proof that the galaxy existed at all. And yet, it's still traveling, still carrying information, still moving through the dark. The universe has already begun its goodbye. The farewell started billions of years ago, and it will continue for trillions more. But it's not a sudden departure. It's a slow, graceful fade, a dimming of lights, a lengthening of shadows. And in that fading, there's a kind of beauty, the beauty of a song coming to an end, the beauty of a story knowing when to close. We're witnesses to this, not victims, witnesses. And maybe that's enough. The stars themselves are watching too, but they're not passive observers. They're participants in the ending burning bright, even as the darkness grows. Stars don't die the way we imagine. There's no sudden blackout, no cosmic switch flipping off. A star's death is measured in millennia, sometimes millions of years. It's a slow dimming, a gradual cooling, like a candle burning down through the night. And in that slow fade, there's something almost tender, as if the universe is giving each star time to say goodbye. Our sun is middle-aged, about 4.6 billion years old, with roughly 5 billion years left to burn. That sounds like forever, but in cosmic terms, it's already past its prime. Right now, it's fusing hydrogen into helium in its core, releasing energy that keeps it shining, keeps Earth warm, keeps life alive. But hydrogen doesn't last forever. When the sun exhausts its core hydrogen about 5 billion years from now, something interesting will happen. The core will contract, heating up, while the outer layers will expand. The sun will become a red giant, swelling so large it might engulf Mercury and Venus. Maybe even Earth. Its surface will cool and redden, but its overall luminosity will increase. For a few 100 million years, it will be a bloated, dying star burning helium in its core instead of hydrogen. And then quietly, it will shed its outer layers, not explosively, but gently, like someone slipping off a coat. Those layers will drift into space, forming what astronomers call a planetary nebula, a glowing shell of gas illuminated by the hot core left behind. That core, no longer fusing anything, will become a white dwarf, a stellar ember, dense, hot, slowly radiating away its remaining heat over trillions of years. White dwarfs are strange objects. They're roughly the size of Earth, but contain about half the mass of the Sun. That makes them incredibly dense. A teaspoon of white dwarf material would weigh about 5 tons. They're held up not by fusion or heat, but by something called electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed any closer together. It's the same force that keeps your hand from passing through a table. Atoms don't like to overlap. And in a white dwarf, that resistance is strong enough to support the mass of half a star. White dwarfs don't shine because they're producing energy. They shine because they're hot. Incredibly hot, tens of thousands of degrees at first. But with no internal furnace to keep them warm, they cool over time. Slowly, very slowly. The coolest white dwarfs we found are still about 3,000 degrees Celsius. That's cooler than the surface of the sun, but still hot enough to glow faintly. And they'll keep cooling over billions and trillions of years until they become black dwarfs, cold, dark, invisible lumps of carbon and oxygen drifting through space. We've never actually seen a black dwarf. The universe isn't old enough yet. Even the oldest white dwarfs still have some heat left. But we know they're coming. In 10 quadrillion years, a 1 followed by 16 zeros, every white dwarf in the universe will have cooled to the point where it no longer emits visible light. They'll become cosmic ghosts, unseen, unfelt, slowly fading into the absolute cold of deep space. But not all stars die this way. Larger stars, those more than about 8 times the mass of the sun, have a different fate. They burn brighter, hotter, and faster, exhausting their fuel in just a few million years. And when they run out, they don't fade quietly. They explode. A supernova is one of the most violent events in the universe. In a matter of seconds, a massive star collapses and then rebounds, blasting its outer layers into space at speeds of up to 10% the speed of light. For a few weeks, a single supernova can outshine an entire galaxy. It's a cosmic shout, a final burst of defiance before the end. On February 23, 1987, astronomers detected a supernova in the Large Magellanic Cloud, a small galaxy orbiting the Milky Way. It was the closest supernova visible to the naked eye since 1604. Designated SN 1987A, it gave scientists an unprecedented opportunity to study a stellar explosion in real time. They watched as the light peak faded and then evolved into a glowing ring of debris, the remnants of the star's outer layers, now expanding into space. But the most remarkable thing about SN 1987A wasn't the light. It was the neutrinos. 3 hours before the visible light arrived, detectors on Earth picked up a burst of neutrinos, ghostly particles that barely interact with matter. These neutrinos were produced in the star's core during the collapse. And because they don't interact much with anything, they escaped almost immediately. Light, on the other hand, had to fight its way out through the star's outer layers, scattering and bouncing, before finally breaking free. The neutrinos arrived first like messengers announcing the death before the body fell. Those neutrinos carried information. They told us that the core of the star had collapsed into something incredibly dense, either a neutron star or a black hole. We still don't know which. The debris from the explosion is too thick for us to see through even now, more than 35 years later. But whatever it is, it's there. A compact remnant, the heart of a star compressed beyond imagination. Neutron stars are almost as strange as black holes. They're about 20 kilometers across, roughly the size of a city, but they contain more mass than the sun. That makes them the densest objects in the universe that aren't black holes. A sugar cube-sized chunk of neutron star material would weigh about 1 billion tons. They're held together by neutron degeneracy pressure, the same quantum effect that supports white dwarfs, but much, much stronger. Some neutron stars spin fast, really fast. The fastest known pulsar, a rotating neutron star that emits beams of radiation like a lighthouse, spins 716 times per second. That's faster than a kitchen blender. Imagine something with more mass than the sun, compressed into a ball the size of Manhattan, spinning hundreds of times every second. And you start to get a sense of how extreme these objects are. Pulsars were discovered by accident in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge. She noticed a strange regular signal in the radio telescope data, a pulse repeating every 1.3 seconds. At first, some researchers jokingly called it LGM1 for Little Green Men, because the signal was so regular it seemed artificial. But further observations revealed the truth. It was a neutron star spinning and beaming radio waves toward Earth like a cosmic metronome. Pulsars slow down over time. As they spin, they emit radiation which carries away energy. That energy has to come from somewhere, and it comes from the rotation. Slowly, over millions of years, pulsars spin down their pulses, lengthening their beams, fading. Eventually, they stop emitting detectable radiation altogether. They're still there, still spinning, but no longer visible. They become quiet neutron stars, cooling and fading, like white dwarfs, just much, much denser. And then there are the stars that collapse so completely that not even neutron degeneracy pressure can stop them. They become black holes. Black holes aren't holes exactly. They're regions of space where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon, and it's a one-way membrane. Cross it, and you can never come back. All paths lead inward toward the singularity at the center, where the laws of physics as we know them break down. The smallest black holes formed from the collapse of massive stars are called stellar mass black holes. They range from a few times the mass of the sun to a few dozen solar masses. They're invisible, of course, but we can detect them by their effects. If a black hole is part of a binary system orbiting another star, it can pull gas from its companion. That gas spirals inward, heating up and emitting X-rays before it crosses the event horizon. We've found dozens of black holes this way, hidden in plain sight, betrayed by the light of matter falling into them. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. It was a supermassive black hole at the center of the galaxy, M87, about 55 million light-years away. The image showed a bright ring of glowing gas surrounding a dark circle, the event horizon. The black hole itself was invisible, but its shadow was clear. It was a moment of profound validation. Something predicted by Einstein's equations over a century ago, finally seen with human eyes. But stellar mass black holes don't stay active forever. Once they've consumed all the nearby matter, they go quiet. They stop accreting gas, emitting X-rays, and become invisible again. They just drift through space, invisible anchors in the cosmic dark, slowly pulling in any matter that wanders too close. Over trillions of years, they'll merge with other black holes, growing larger, more massive, until eventually they're the last massive objects in the universe. There's something poetic about the death of stars. The small ones, like the sun, fade gently, leaving behind glowing embers that cool over eons. The large ones explode, scattering their ashes across space, seeding the next generation of stars with heavy elements. And the largest ones collapse into singularities, becoming eternal prisoners of their own gravity. Each death is different. Each one leaves a different kind of trace. But they all end in silence, in stillness, in a slow drift toward equilibrium. Have you ever watched a fire burn down? At first it's bright and hot, crackling and dancing. But as the night goes on, the flames settle, the wood turns to coals, the heat fades. Eventually there's just ash and warmth, and then not even that. Just the memory of light. That's what stars are doing. All of them. Burning, fading, leaving traces. And in a universe that's accelerating apart, those traces will grow fainter and farther apart. One day the last star will burn out. The last white dwarf will cool. The last neutron star will stop spinning. And the universe will be left with only black holes drifting in an ever-expanding void. But we're not there yet. Not even close. Right now, stars are still being born. Nebulae are still collapsing under their own gravity, igniting fusion in their cores, lighting up the dark. The universe is still young enough for light, still warm enough for life, still alive with the glow of 1 trillion suns. And those suns are teaching us something. That endings don't have to be violent to be beautiful. That a slow fade can be just as profound as a sudden explosion. That there's grace in cooling dignity, in silence, peace in the long, quiet descent into the dark. But even black holes, those final remnants, those seeming eternal monuments to collapsed stars, they won't last forever either. They too will fade in ways stranger than we ever imagined. Imagine a cup of coffee, freshly poured steam rising in delicate spirals. You don't drink it right away. You let it sit. And slowly, imperceptibly, it cools. The heat doesn't disappear, it spreads into the air, into the table, into the room. Eventually, the coffee reaches room temperature. No more steam, no more warmth, just equilibrium. And once it's there, nothing happens anymore. No flow of heat, no change, just stillness. That's the fate of the universe. Not a dramatic explosion or a violent collapse, but a slow, inevitable cooling. A drift toward perfect equilibrium, where no energy flows, no work gets done, and nothing, absolutely nothing, can happen ever again. Scientists call it the heat death, and it's the most likely ending we face. The concept emerged in the 19th century long before we understood the expanding universe or dark energy. It grew out of a branch of physics called thermodynamics, the study of heat energy and how they flow from one place to another. The second law of thermodynamics, formulated by Rudolf Clausius and William Thomson in the 1850s, states something simple but profound. In any closed system, entropy always increases. Entropy is often described as disorder, but that's not quite right. It's better to think of it as evenness, uniformity, a measure of how spread out energy is. When you pour hot coffee into a cold room, the heat doesn't stay in the cup. It spreads. The coffee cools. The room warms slightly, and eventually everything reaches the same temperature. That's entropy increasing, energy spreading out, becoming more evenly distributed, less useful for doing work. And the universe is a closed system, the largest closed system we know. There's nothing outside it to add energy, no external source to reset the balance. So entropy keeps increasing, energy keeps spreading out, and one day far, far in the future, everything will reach the same temperature, the same low-cold uniform state. And then nothing will happen. Ever again. This is the heat death. Not death in the sense of destruction, but death in the sense of stillness. Maximum entropy. Perfect equilibrium. A universe where every region has the same temperature, the same energy density, the same nothing. Let's walk through how we get there. Right now, the universe is full of temperature differences. Stars are hot, millions of degrees in their cores. The space between stars is cold, just a few degrees above absolute zero. That difference drives everything. Heat flows from hot to cold. Stars radiate energy. Planets warm in their glow. Life emerges in the narrow bands where temperatures are just right. All of it depends on the fact that the universe is not yet in equilibrium. But stars don't burn forever. As we've seen, they exhaust their fuel and die. Some become white dwarfs. Some explode as supernovae. Some collapse into black holes. And with each death, the universe loses a source of heat, loses a driver of change. In a few trillion years, 13 years, give or take, the last conventional star will flicker out. The universe will enter what cosmologists call the degenerate era. No more fusion, no more starlight. Just the fading embers of dead stars, white dwarfs, brown dwarfs, neutron stars slowly radiating away their remaining warmth into the void. White dwarfs, as we discussed, cool very slowly. They start at tens of thousands of degrees and take trillions of years to cool to a few thousand, then trillions more to cool to hundreds. Eventually, they'll reach the temperature of the cosmic microwave background, the faint glow left over from the Big Bang, which right now is about 2.7 degrees above absolute zero. But here's the thing, the cosmic microwave background is cooling too, as the universe expands the wavelengths of that ancient light stretch, shifting toward longer, redder, lower energy wavelengths. The temperature of the background drops. Right now it's 2.7 Kelvin. In a trillion years, it might be 0.3 Kelvin. In 100 trillion years, even colder. Eventually, it will approach absolute zero. Not quite reaching it, but getting so close the difference hardly matters. And the white dwarfs cooling alongside it will eventually match that temperature. They'll stop radiating detectable heat. They'll become black dwarfs, cold, dark, inert lumps of carbon and oxygen drifting through an equally cold and dark space. The universe won't be completely empty, though. There will still be matter, protons, electrons, neutrinos, photons, all the fundamental particles spread thin across an unimaginable volume, but they'll all be moving slowly. Quantum mechanics tells us that even at absolute zero, particles still have some motion zero-point energy, the irreducible jitter of the quantum world. But for all practical purposes, everything will be still. No more stars, no more planets, no more galaxies as we know them. Just isolated black dwarfs, neutron stars, and black holes scattered across a vast, cold, expanding void. And at this point, you might think, well, at least there are still black holes. At least something massive and interesting remains. But even black holes don't last forever. In 1974, Stephen Hawking made a discovery that shocked the physics community. He showed using quantum mechanics and general relativity that black holes aren't entirely black. They emit radiation. Very faint radiation, but real nonetheless. This radiation, now called Hawking radiation, comes from quantum effects near the event horizon. Virtual particle pairs pop into existence at the edge of the black hole, and occasionally one particle escapes while the other falls in. To an outside observer, it looks like the black hole is radiating, but this radiation carries energy, and that energy has to come from somewhere. It comes from the black hole's mass. Over time, as the black hole radiates, it loses mass. It shrinks, slowly at first, excruciatingly slowly. For large black holes, but inevitably. How slowly a black hole with the mass of the sun would take about 1,067 years to evaporate. That's a 1 followed by 67 zeros, a number so large it's hard to even visualize. For comparison, the current age of the universe is about 10,110 years, so a solar mass black hole would take 10 quadrillion times the current age of the universe to evaporate. Supermassive black holes, the kind at the centers of galaxies with millions or billions of solar masses, take even longer. The black hole at the center of the Milky Way Sagittarius A has about 4 million times the mass of the Sun. It would take roughly 1099 years to evaporate. That's a 1 followed by 99 zeros. A span of time so vast it makes eternity feel quaint. But time doesn't care how vast the numbers are. Time just keeps passing. And eventually, even the largest black holes will shrink. As they lose mass, they radiate faster. The smaller they get, the hotter they become. In the final moments, if you can call billions of years moments, a black hole will radiate intensely, releasing all its remaining mass energy in a final burst before vanishing completely. What's left after a black hole evaporates? Nothing. Just radiation. Photons and other particles scattered into the void, their energy too diffuse to ever recombine into anything meaningful. So, by the time we reach 10,100 years, a Google years, if you like big numbers, the universe will be a cold, dark, empty expanse. No stars, no black holes, just a faint soup of photons, neutrinos, and maybe a few stray electrons and positrons, all drifting through space at nearly absolute zero. This is the heat death, maximum entropy, perfect equilibrium. No energy gradients to drive processes, no way to extract useful work. The universe will still exist, but nothing will happen. No change, no motion. No time in any meaningful sense, because time only matters when things change. Some people find this depressing. The idea that everything, all the stars, all the galaxies, all the beauty and complexity we see, will one day fade into a featureless void. But there's another perspective. The heat death is peaceful. It's rest. True rest. After 100 years of cosmic drama, stars igniting and dying, galaxies colliding, black holes devouring matter, the universe finally gets to sleep. And maybe that's not a tragedy. Maybe that's exactly what the universe needs. Think about your own life. You work, you struggle, you create, you love, you lose. And at the end of the day, what do you want? Rest. Sleep. A chance to stop moving, stop thinking, stop being anything for a while. The universe is no different. It's been expanding, evolving, burning for nearly 14 billion years. It deserves to rest. There's also something humbling about the heat death. It reminds us that we're temporary, not just as individuals, but as a species, as a planet, as a galaxy. Everything we build, everything we achieve, will one day be forgotten. Not because no one remembers, but because there will be no one left to remember, no minds, no consciousness, no light to see by. But does that make our achievements meaningless? Does the fact that the universe will end make your life less valuable? Some philosophers say yes. If everything ends in heat death, nothing we do matters. But I think that misses the point. Meaning doesn't come from permanence, it comes from experience. From the fact that right now, in this moment, you exist. You feel, you think, you wonder, and that's enough. The universe is dying, yes. Slowly over time scales so vast they border on the infinite. But it's not dead yet. Right now, stars are shining, galaxies are forming. Life is evolving on countless worlds we haven't even discovered. And somewhere on a small blue planet, people are lying in bed, listening to stories about the end of everything, and finding comfort in the knowledge that endings are natural, necessary, beautiful. The heat. Death isn't a failure, it's a completion. The universe started with a bang, hot, dense, chaotic. And it will end in a whisper, cold, thin, still, from fire to ice, from noise to silence, from everything to almost nothing. And in that almost nothing, there might still be something. Because even in the far future, even at maximum entropy, quantum fluctuations will still occur. Tiny random variations in the vacuum. Most of them will fizzle out immediately. But over enough time, truly unimaginable time, something might happen. A fluctuation might grow. A new universe might bubble into existence. Or maybe not. Maybe the heat death is final. We don't know yet. We might never know. But we can imagine. We can calculate. We can peer into the equations and see what they suggest. And what they suggest is rest. The long, deep rest that comes after a life well lived. The universe has given us stars, galaxies, planets, life. It's given us beauty and wonder and mystery. And when it's done, when every last photon has redshifted into oblivion and every last particle has drifted beyond the horizon, it will finally truly rest. But before the universe reaches that final stillness, before it cools into eternal silence, there are still the black holes, those strange survivors, those cosmic monuments that seem to defy time itself. Yet even they must answer to entropy's patient hand. Black holes are the universe's most patient predators. They don't chase, they don't hunt, they just wait. Gravity does the work, pulling everything closer, slowly, inevitably, until it crosses a line from which there's no return. And once something falls in, it's gone. Not destroyed exactly, just removed from the universe we can observe, hidden behind a veil we can never lift. For a long time, physicists thought black holes were eternal, immortal monuments to collapsed stars growing larger with every meal, never shrinking, never fading. But in 1974, Stephen Hawking discovered something that changed everything. Black holes evaporate, they lose mass, and given enough time, enough unimaginable, unfathomable time, they vanish completely. Hawking didn't expect this result. He was studying quantum mechanics near the event horizon, trying to understand what happens to particles in the intense gravitational field of a black hole. And he found something strange. Black holes aren't perfectly black. They glow, faintly, almost imperceptibly, but they glow. The mechanism is subtle. In the vacuum of space, quantum mechanics allows pairs of particles to pop into existence for the briefest of moments, a particle and its antiparticle borrowing energy from the vacuum, existing just long enough to annihilate each other and repay the debt. These are called virtual particles, and they appear everywhere all the time, though we can't detect them directly. But near the event horizon of a black hole, something unusual can happen. If a particle pair forms right at the edge, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole emitted a particle. This is Hawking radiation. Here's the catch. The escaping particle carries energy, and energy, according to Einstein's famous equation, is equivalent to mass. So, when a particle escapes the black hole, loses a tiny bit of mass. It gets smaller. And this process continues slowly, relentlessly, for as long as the black hole exists. For large black holes, Hawking radiation is extraordinarily weak. A black hole with the mass of the Sun emits radiation at a temperature of about 60 nanokelvins. That's 60 billionths of a degree above absolute zero. Far colder than the cosmic microwave background, which is currently about 2.7 Kelvin. So right now, black holes are actually absorbing more energy from the background radiation than they're emitting. They're growing, not shrinking. But the cosmic microwave background is cooling as the universe expands. Eventually, it will drop below the temperature of Hawking radiation. And when that happens, black holes will start to lose mass, slowly at first. A solar mass black hole would take about 1,067 years to evaporate completely. That's far longer than the current age of the universe, far longer than the time it takes for stars to die out, far longer than most people can imagine. Supermassive black holes take even longer. The black hole at the center of our galaxy, Sagittarius AY, would take roughly 1099 years to evaporate. And the largest black holes we've detected, monsters with tens of billions of solar masses, would take even longer. 100 years, give or take. A Google years. A timescale so vast that writing it out would take more digits than there are atoms in the observable universe. But time doesn't stop. And Hawking radiation doesn't either. Over those unimaginable eons, black holes will shrink, bit by bit, particle by particle. And as they shrink, they get hotter. This is counterintuitive. You'd think a smaller black hole would be colder, but the opposite is true. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A black hole with the mass of the Sun has a temperature of 60 nanokelvins. A black hole with half that mass has double the temperature. And a black hole with the mass of a mountain might have a temperature of a few degrees. A black hole the size of a bacterium could be millions of degrees. As black holes evaporate, they radiate faster and faster. What starts as a trickle becomes a stream, then a torrent. In the final moments of a black hole's life, it releases an enormous burst of energy, a flash of gamma rays, particles radiation, before vanishing completely. We've never observed this, of course. No black hole has existed long enough to evaporate. But the math is clear. And Stephen Hawking's equations have been tested in other ways through analog systems, laboratory experiments, observations of particle physics, and they hold up. Hawking radiation is real. Black holes are mortal. So here's what the far future looks like. After the last stars have died, after the white dwarfs have cooled, after the neutron stars have stopped spinning, the universe will be dominated by black holes. They'll be the last massive objects, the last remnants of structure in an otherwise empty cosmos. For a while, a very long while, they'll just drift. Isolated islands of intense gravity separated by unimaginable distances, each one slowly evaporating in the dark. Most of them will never encounter another object. Space is expanding too fast. The gaps between black holes will grow wider and wider, faster and faster, until even light can't bridge the distance. But black holes aren't completely inactive. Even in isolation, they'll still be evaporating. And as they shrink, strange things happen. When a black hole gets small enough around the mass of a large asteroid, it starts to radiate particles we can detect. Photons, neutrinos, electrons, positrons. These particles fly off in all directions, carrying away the black hole's mass energy. The black hole glows, not with reflected light, but with its own light. Light born from gravity, from the collapse of space itself. And then, in the final microseconds, the black hole explodes. Not violently in the way we think of explosions. There's no shock wave, no debris field, but energetically. All the remaining mass converts to radiation in an instant. A final flash, a last breath. And then nothing. Just photons and particles scattering into the void, their energy too diffuse to ever recombine. This is the ultimate fate of every black hole. Not eternal monuments, but temporary structures. Candles burning in the dark, lasting far longer than any star, but still finite, still mortal. What's remarkable is that this process, Hawking radiation, is both quantum and gravitational. It involves both the smallest scales of physics and the largest. It's a bridge between two theories that don't usually play well together. Quantum mechanics describes the behavior of particles. General relativity describes the behavior of space-time, and Hawking radiation requires both. It's one of the few places where we can see quantum mechanics and gravity working together, hinting at a deeper theory we haven't fully understood yet. Some physicists hope that studying Hawking radiation will lead to a theory of quantum gravity, a unified framework that explains both the quantum world and the gravitational world in a single elegant set of equations. Others think black holes might be the key to understanding the information paradox, one of the deepest mysteries in modern physics. The information paradox goes like this. In quantum mechanics, information is never truly destroyed. If you know the exact state of a system at one moment, you can in principle calculate what it will be at any other moment. Even if something burns or dissolves or decays, the information about its original state is preserved in the particles and radiation it leaves behind. But what happens when something falls into a black hole? The information about that object seems to disappear. It crosses the event horizon and we can never retrieve it. If the black hole then evaporates via Hawking radiation, where does the information go? The radiation seems random thermal, devoid of any information about what fell in. So, is information destroyed? Stephen Hawking originally thought the answer was yes. Information is lost. But that violates a fundamental principle of quantum mechanics. Other physicists disagreed. Debates raged for decades. Conferences were held, bets were made. And gradually a consensus emerged. Information is not destroyed. It's encoded somehow in the Hawking radiation in ways we don't yet fully understand. The black hole remembers what it ate even if we can't decode the message. This is still an active area of research. Physicists are exploring ideas like holography, the notion that all the information inside a black hole is encoded on its two-dimensional event horizon, like a hologram encoding a three-dimensional image. Others are studying string theory loop quantum gravity and other frameworks that might explain how information escapes. But for our purposes, what matters is this. Black holes are not eternal. They're not infinite sinks where matter disappears forever. They're temporary, finite, and in the end, they give everything back, not in the form they received it, but as radiation, as energy, as photons scattered into the expanding void. After 10 to 100 years, when the last black hole evaporates what's left. A universe filled with low-energy photons, neutrinos, and maybe a few stray electrons and positrons. No stars, no planets, no galaxies, no structure of any kind. Just a faint cold soup of particles spread so thin that most of them will never interact with anything ever again. It sounds bleak, empty, lifeless. But there's a kind of purity to it, a simplicity. The universe started as a hot, dense plasma particles colliding energy, transforming chaos everywhere. And it will end as a cold, diffuse gas particles drifting energy, fading stillness everywhere. From fire to ice, from noise to silence, from complexity back to simplicity. And maybe that's fitting. Maybe that's how stories should end. Not with a bang, but with a sigh. Not with a climax, but with a resolution. The universe will have done everything it could do. Created stars, galaxies, planets, life, thought. And then, when there's nothing left to create, it will rest. Black holes are the last act in this cosmic drama, the final players on the stage. And when they take their bow and exit, the curtain falls. The lights dim. The audience, if there is one, goes home. But here's the question. Is that really the end? Is heat death the final word? Or is there something else? Some loophole in the equations, some possibility we haven't considered? Because even in the far future, even at maximum entropy, the universe might still have a few tricks left. Quantum mechanics is full of surprises. And if there's one thing we've learned, it's that the cosmos rarely follows our expectations. So, let's explore the possibilities, the different ways this story might conclude, each with its own kind of beauty, its own quiet logic. The universe doesn't know how it will end. Or maybe it does, and we're the ones still guessing. For decades, cosmologists have mapped 3 possible futures, 3 different finales written in the equations of general relativity and quantum mechanics. Each one sounds catastrophic. The big freeze, the big rip, the big crunch. But when you look closer, when you let the physics settle quietly into understanding, you realize something unexpected. These aren't disasters, they're transformations. 3 different ways for a story to close, each with its own strange grace. We've already explored the big freeze, the slow, cooling the drift toward maximum entropy, the long fade into stillness. But it's worth placing it alongside its siblings to see how they compare, to understand what tips the balance from one ending to another. The fate of the universe depends on 3 things: the density of matter and energy, the strength of dark energy, and the shape of space-time itself. Change any of these variables even slightly, and you change the ending. Let's start with the Big Crunch. This was the ending cosmologists favored before the discovery of dark energy in 1998. The logic was simple. The universe is expanding now because of the Big Bang, the initial explosion that set everything in motion. But gravity is pulling everything back together. So the question became, is there enough matter in the universe for gravity to eventually win? If the universe is dense enough, if there's enough mass to overcome the expansion, then eventually the outward motion will slow stop and reverse. Galaxies will start moving toward each other instead of away. The cosmic microwave background will blue shift instead of redshift, growing hotter as space contracts. Stars will merge, galaxies will collide, and eventually everything will collapse back into a singularity, a reverse Big Bang, the Big Crunch. In the early 20th century, this seemed elegant, symmetrical. The universe begins with an explosion and ends with an implosion. Birth and death mirror each other. Some physicists even imagine that the Big Crunch might trigger another Big Bang, a cyclic universe bouncing eternally between expansion and contraction like a cosmic heartbeat. But the discovery of dark energy changed everything. Observations of distant supernovae in 1998 showed that the universe's expansion isn't slowing down, it's speeding up. Something is pushing space apart, and that something is stronger than gravity. The Big Crunch became unlikely, not impossible, but improbable. For it to happen, dark energy would have to weaken or reverse at some point in the future. And while we can't rule that out, we don't fully understand what dark energy is. There's no evidence suggesting it will. So, the Big Crunch remains a theoretical possibility, a road not taken, a future that might have been, but probably isn't. Still, let's imagine it. Let's drift into that other timeline and see what it would feel like. At first, nothing changes. Galaxies continue moving apart just as they do now. Stars are born, live, and die. Planets orbit their suns. Life evolves if it hasn't already. For billions of years, maybe trillions, the universe looks much like it does now. But slowly, imperceptibly, the expansion begins to slow. Scientists in that future universe would notice it first in their measurements. The redshift of distant galaxies would decrease. The cosmic microwave background would stop cooling and begin to warm. At first, the changes would be subtle fractions of a degree, tiny shifts in wavelength. But over time, they would become undeniable. The universe is contracting. Galaxies that had been receding would halt, then reverse course. The Andromeda Galaxy, which in our timeline is on a collision course with the Milky Way in about 4 billion years, would accelerate toward us even faster. Other galaxies currently too distant to ever reach us would start closing the gap. The universe would become more crowded, more connected. For a while, this might seem like a blessing. Isolation reversed, the cosmic horizon shrinking, bringing distant galaxies back into view. Future astronomers would have more to study, not less. More galaxies, more stars, more phenomena within reach. But as the contraction continues, things get hotter. The cosmic microwave background, currently at 2.7 Kelvin, would warm, first to room temperature, then to the boiling point of water, then to thousands of degrees. Space itself would become inhospitable. Any planet still harboring life would cook. Oceans would boil away. Atmospheres would strip. Life, if it still exists, would face an existential crisis. Eventually, galaxies would merge, not gracefully as in our timeline, but violently, rapidly as space collapses around them. Stars would collide more frequently. Gas clouds would compress and ignite. The universe would become a furnace, growing brighter and hotter as everything rushes toward the center. And then, in the final moments, if moments can even be defined, when space-time itself is collapsing, everything converges. All matter, all energy, all space-time collapsing into a singularity. Infinite density, infinite temperature, a reversal of the Big Bang, the clock running backward, the universe inhaling after its long exhale. What happens next? Does the singularity explode again, triggering a new Big Bang? Or does it remain compressed forever, a cosmic endpoint with no sequel? We don't know. The equations break down at singularities. General relativity stops making predictions. Quantum mechanics offers hint suggestions that the singularity might bounce, might create new space-time, but no definitive answers. The Big Crunch is peaceful in its own way. Not the peace of cooling and stillness, but the peace of return, of coming home. Everything that was scattered by the Big Bang reunited. Separated particles brought back together. It's an ending that feels complete, symmetrical, a closing of the circle. But it's probably not our ending. Now let's consider the Big Rip. This is the most violent of the three scenarios and the most speculative. It depends on a specific kind of dark energy one that not only pushes space apart, but accelerates over time, growing stronger and stronger until it overcomes every force holding things together. Most cosmological models assume dark energy is constant. the same strength everywhere at all times. This is called the cosmological constant, and it leads to the big freeze. But what if dark energy isn't constant? What if it's a field, something dynamic, something that can change? If dark energy strengthens over time, the expansion of the universe accelerates faster and faster. Eventually, it accelerates so much that it starts tearing things apart. Not just galaxies and stars, but planets, molecules, atoms, even the fabric of space-time itself. This is the Big Rip. The process would be gradual at first. Galaxies would drift apart just as they do now, but faster. Galaxy clusters, groups of galaxies held together by gravity would dissolve. Individual galaxies would lose their outlying stars, their spiral arms unraveling as dark energy pulls them apart. About 60 million years before the rip, the Milky Way would disintegrate. Stars would fly off into the void, no longer bound to the galactic core. 3 months before the rip, solar systems would unbind. Earth would drift away from the sun, following its own trajectory through the dark. 30 minutes before the rip, planets themselves would shatter. The gravitational force holding Earth together would be overwhelmed by the expansion of space. Chunks of rock and metal would scatter, each piece following its own path, never to recombine. And then, in the final moments, atoms would tear apart. Electrons ripped from their nuclei, protons and neutrons disassembled into quarks. Even the quarks themselves might not survive. Space would be expanding so fast that nothing could hold together. The universe wouldn't just be empty, it would be fragmented, dissolved, broken down into its most fundamental components. And then, the equations predict a singularity. Not a collapse like the Big Crunch, but a rupture. A moment when the expansion becomes infinite, when space-time itself tears. What lies beyond that moment, no one knows. The math stops working. The story ends mid-sentence. The Big Rip sounds horrifying, violent, an ending by force, by disintegration. But there's a strange beauty to it too. It's an ending that insists nothing lasts. Not galaxies, not stars, not even atoms. Everything dissolves. Everything returns to simplicity. In a way, it's the ultimate expression of impermanence. The universe doesn't just die, it completely lets go. Fortunately, current observations suggest the Big Rip is unlikely. Measurements of dark energy show no sign that it's strengthening. It appears constant or close to it. But we've only been measuring for a few decades. Dark energy might change on timescales far longer than we can observe. So, the Big Rip remains a possibility. Distant, improbable, but not impossible. Which brings us back to the Big Freeze, the ending we've been circling, the one most consistent with current data, the slow cooling, the drift toward maximum entropy, the long fade into stillness. The Big Freeze doesn't tear anything apart. It doesn't compress anything. It just spreads everything out, thinner and thinner, colder and colder, until nothing can happen anymore. Stars burn out. Black holes evaporate. Particles drift through an empty, expanding void. And eventually, the universe reaches a state where no energy flows, no work gets done, no change occurs. It's the least dramatic of the three endings. No implosion, no explosion, no rupture, just a slow, gentle stop. Like a song fading to silence, like a conversation trailing off, like falling asleep at the end of a long day. And maybe that's why it feels right, because it matches the rhythm we see everywhere in nature. Things don't usually end with violence. They end with exhaustion, with entropy, with the gradual loss of the ability to keep going. A fire burns down, a wave dissipates, a star cools, and the universe, having burned for trillions of years, finally runs out of fuel. 3 endings, 3 possibilities, each one a reflection of the forces shaping our cosmos. Gravity pulling inward, dark energy pushing outward, and matter caught between them, shaping the story. Which one is real? We think we know. The Big Freeze seems most likely. But the universe has surprised us before, and it might surprise us again. What matters, perhaps, is not which ending we get, but that we can imagine all three, that we can look at the equations and see futures written in mathematics, that we can sit quietly under the stars and contemplate the end of everything with curiosity instead of fear. Because no matter how the universe ends, it hasn't ended yet. And that gives us time. Time to wonder, time to explore, time to ask the next question. Which is, this what if the end isn't really the end? What if there's something after, some loophole, some possibility, some continuation we haven't considered? Let's find out. What if the end isn't final? What if the universe, after cooling into silence, after fading into maximum entropy, after reaching that perfect stillness, we call heat death? What if it stirs again, not immediately, not dramatically, but slowly, quietly, the way morning light creeps through curtains after the longest night? What if endings are just pauses? What if death is just deep sleep? This isn't wishful thinking, it's physics. Strange physics, speculative physics, but physics nonetheless. Because even at maximum entropy, even in the coldest, emptiest possible universe, quantum mechanics whispers a possibility. Things can still happen. Fluctuations, variations, tiny deviations from perfect uniformity. And over enough time, truly unimaginable spans of time, those fluctuations might grow into something new. The idea of a cyclic universe isn't new. Ancient cultures imagined time as circular. The Hindus spoke of cosmic cycles, creation, preservation, destruction, and rebirth repeating endlessly. The Stoics in ancient Greece believed the universe would eventually return to fire, only to be reborn again. But these were philosophical ideas, spiritual intuitions, not science. Then in the early 2000s, physicists began taking cyclical cosmology seriously again. Not because of ancient wisdom, but because of modern problems. Specifically problems with the Big Bang. The Big Bang theory is incredibly successful. It explains the expansion of the universe, the cosmic microwave background, the abundance of light elements. But it doesn't explain what caused the Big Bang, or what came before it. General relativity predicts a singularity, a point of infinite density. But singularities are places where the equations break down. They're like errors in the code, spots where the universe says, "I don't know what happens here." Some physicists found this unsatisfying, and they started asking, what if the Big Bang wasn't the beginning? What if it was just a transition, a bounce, a moment, when a previous universe collapsing under its own gravity reached maximum compression and then rebounded? This is the core idea behind cyclic cosmology. The universe expands, contracts, compresses into a singularity, and then bounces, triggering a new Big Bang, a new expansion, a new cycle. And this process repeats perhaps eternally, each cycle lasting trillions of years, each one creating stars, galaxies, planets, maybe life, and each one ending only to begin again. One prominent model is called conformal cyclic cosmology, proposed by the physicist Roger Penrose. Penrose is a mathematical physicist, a colleague of Stephen Hawking, and he's known for thinking deeply about the nature of time and space-time. His idea is subtle, elegant, and a little mind-bending. Penrose suggests that the far future of our universe, after all the black holes have evaporated, after everything is decayed into massless particles like photons, looks mathematically similar to the very early universe just after the Big Bang. In both cases, you have a universe filled with massless particles, no structure, no complexity. And Penrose argues that you can smoothly connect these two states. The end of one universe becomes the beginning of the next. Here's how it works. In the far future, after 10 to 100 years or so, the universe is cold, empty, and filled only with photons and other massless particles. These particles have no sense of time. Photons don't experience time from their perspective. They exist everywhere along their path simultaneously. And in a universe with only massless particles, there's no way to measure time or scale. Penrose calls this a conformal state, where the geometry of space-time can be stretched or compressed without changing its essential structure. And he suggests that this far future state can be mathematically transformed into the hot, dense state of a new Big Bang. The end loops back to the beginning, not physically, but geometrically. The universe forgets its size, forgets its age, and resets. It's a beautiful idea, mathematically elegant, but it's also speculative. We don't have direct evidence for it. We don't know if the universe actually behaves this way. But the equations allow it, and that's enough to make it worth considering. There are other cyclic models too. Some involve extra dimensions, hidden realms, beyond the 3 dimensions of space and one, of time that we experience. String theory, for example, suggests the universe might have 10 or 11 dimensions, most of them curled up so small we can't detect them. In some versions of string theory, our universe is a 3-dimensional brain, short for membrane, floating in a higher dimensional space. And occasionally, our brain collides with another brain, triggering a Big Bang-like event. These collisions could repeat cyclically, creating new universes again and again. Another possibility involves quantum fluctuations. Even in a universe at maximum entropy, quantum mechanics predicts that random fluctuations will occur. Most of them are tiny virtual particles, appearing and disappearing in the fractions of a second. But over vast stretches of time, larger fluctuations become possible. Maybe after 10 5 to 6 years, a number so large it's almost meaningless, a fluctuation large enough to create a new universe might occur. A bubble of space-time inflating, rapidly giving birth to stars and galaxies and everything else. This is sometimes called a Boltzmann universe, named after the physicist Ludwig Boltzmann, who studied entropy and statistical mechanics in the 19th century. Boltzmann understood that in a system at maximum entropy, fluctuations away from equilibrium are possible, though rare. And he realized that if you wait long enough, truly cosmically long, even large fluctuations become probable. The catch is that these fluctuations are far more likely to produce small, simple structures than large, complex ones. It's more probable that a single galaxy would randomly fluctuate into existence than an entire universe. More probable that a single brain would spontaneously assemble than a planet full of life. These hypothetical brains, called Boltzmann brains, are a strange consequence of the math. They're troubling for some physicists because if most conscious observers in the far future are Boltzmann brains, random fluctuations with false memories and no real history, then we can't trust our own observations. We might be Boltzmann brains ourselves with illusory memories of a universe that never actually existed. Most cosmologists think this is unlikely. They argue that our universe is too ordered, too structured, too consistent to be a random fluctuation. But the possibility lingers, a strange footnote in the story of the far future. Still, the broader point remains. Even at maximum entropy, the universe might not be truly dead. Quantum mechanics ensures that the vacuum is never truly empty. Space seethes with virtual particles, temporary violations of energy conservation, brief flickers of something from nothing. Most of these fluctuations are tiny, insignificant. But in an infinite expanse of time, anything that's possible becomes probable, even a new universe. So maybe the heat death isn't the end. Maybe it's a waiting room, a pause, a long, dark intermission before the next act begins. Or maybe not. Maybe the universe ends once and never returns. Maybe entropy wins, and that's the final word. No second chances, no encores, just an eternal, unchanging void. We don't know yet. The math gives us possibilities, not certainties. And that's both frustrating and beautiful. Frustrating because we want answers. Beautiful because it leaves room for wonder. There's another idea worth mentioning. The multiverse. Not cyclical, but parallel. The notion that our universe is just one of many, perhaps infinitely many each, with its own laws of physics, its own history, its own fate. Some of these universes might collapse quickly, others might expand forever. Some might have stars and galaxies. Others might be empty or filled with exotic particles we can't imagine. The multiverse arises naturally in some versions of inflation theory, which describes the rapid expansion of the universe in the first fraction of a second after the Big Bang. Inflation suggests that different regions of space might stop inflating at different times, creating pocket universes with different properties. From the outside, they'd be separate, but they'd all exist within a larger, eternally inflating space. If the multiverse is real, then the end of our universe is just the end of our universe. Not the end of everything. Other universes would continue, each following its own trajectory, each telling its own story. Some might be ending just as ours is beginning. Others might be ancient, trillions of years old, already cold and dark. And still others might be young, just forming their first stars. It's a dizzying thought, humbling. If the multiverse exists, we're not just small within our universe, we're small within a vast ensemble of universes, most of which we can never observe, never visit, never know. But here's what's remarkable. Even if the multiverse is real, even if our universe is just one bubble in an infinite foam that doesn't diminish its value, this is still our universe. These are still our stars. This is still the only reality we can experience. And the fact that it will end, whether in heat death big rip or big crunch, doesn't make it less meaningful. If anything, it makes it more precious. Because endings give shape to stories. They give weight to moments. If the universe lasted forever, unchanged and unchanging, would anything matter? Would there be any reason to look up at the stars and feel wonder? Would there be any urgency to understand, to explore, to connect? Impermanence is what makes things beautiful. The cherry blossoms that bloom for just a few weeks. The sunset that lasts only minutes. The life that flickers for a few decades in a universe that's existed for billions of years. We know these things are temporary, and that's what makes them worth cherishing. The universe is the same, it's temporary. Whether it lasts another 100 years or somehow cycles into a new beginning, it's still finite in a way we can feel. And that finitude is what gives it meaning. So, what comes after the end? Maybe nothing. Maybe something. Maybe a new universe born from quantum fluctuations or conformal geometry or brain collisions. Maybe an infinite multiverse with countless other stories unfolding in parallel. Or maybe just silence. Deep, eternal silence. We don't know. And maybe that's okay. Maybe not knowing is part of the experience, part of being human, part of living in a universe that's bigger and stranger than we can fully comprehend. What we do know is this. Right now the universe is alive. Stars are shining. Galaxies are forming. Life is evolving. Thoughts are happening. And somewhere on a small blue planet, people are lying in bed, listening to stories about the end of everything, and finding comfort in the knowledge that endings are natural, necessary, beautiful. The end might not be the end. But even if it is, even if the universe truly dies and never returns, there's something profound about that too. Something worth honoring. Because in its long, slow journey from birth to death, the universe gave us this. Gave us a moment to exist, to think, to wonder, to love. And maybe that's enough. But before we rest in that knowledge, before we accept the ending with open hands, there's something else we need to understand, why all this impermanence and finitude might actually be the source of beauty itself. There's a Japanese phrase, mono no aware, that doesn't translate cleanly into English. Literally, it means the pathos of things, or an empathy toward things. But what it really describes is the bittersweet awareness that everything is temporary, the gentle sadness and simultaneous joy that comes from knowing something beautiful won't last. Cherry blossoms bloom for 2 weeks, maybe 3, and then they fall. And it's the falling that makes them precious. This isn't pessimism. It's not despair. It's something deeper, a recognition that beauty and impermanence are inseparable, that the things we love are valuable precisely because they're fleeting. Would you watch a sunset with the same attention if it lasted forever? Would you hold someone close if you knew you'd never have to let go? The end of the universe is mono, no aware on the largest possible scale, the ultimate impermanence. And maybe that's what makes it beautiful. We spend so much of our lives avoiding endings. We cling to youth, to health, to relationships, to moments we wish could last forever. We build monuments meant to outlive us. We write stories, create art, have children, all attempts to leave something behind to cheat mortality in some small way. And there's nothing wrong with that. It's human, natural. The desire to matter, to last, to be remembered. But the universe doesn't share our anxiety about endings. It doesn't resist. It doesn't cling. It simply unfolds according to the laws of physics, moving steadily from order to entropy, from complexity to simplicity, from beginning to end. And there's a kind of wisdom in that, a kind of peace. Buddhism teaches the concept of anicca impermanence, one of the three marks of existence alongside suffering and non-self. Everything that arises will cease. Everything that's born will die. Every mountain will erode. Every ocean will evaporate. Every star will burn out. And resisting this truth, clinging to permanence, is the root of suffering. But accepting impermanence, that's liberation. Not because it makes the pain go away, but because it shifts your relationship to it. When you know something is temporary, you pay attention differently. You savor it. You notice details you might otherwise overlook. You stop waiting for the perfect moment and realize that this moment right now is all you have. The universe is teaching us this lesson on the grandest scale imaginable. It's showing us that nothing lasts. Not stars, not galaxies, not even space-time itself. And that's not a tragedy. It's an invitation. An invitation to appreciate what exists now while it still exists. Carl Sagan understood this. In his book Pale Blue Dot, he reflected on a photograph of Earth taken by the Voyager 1 spacecraft from 3.7 billion miles away. In that image, Earth is just a tiny speck, less than a pixel suspended in a beam of sunlight. And Sagan wrote about how that perspective, seeing our planet as fragile, small, temporary, should inspire humility and compassion. Because if Earth is that small, and if everything we've ever known is confined to that pale blue dot, then our conflicts, our hatreds, our petty divisions seem absurd. What matters is that we're here together on this temporary stage. Sagan also said, "We are a way for the cosmos to know itself." Think about that. The universe is not separate from us. We're made of it. Every atom in your body was forged in the heart of a star. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it came from stars that lived billions of years ago, burned through their fuel, and exploded, scattering their ashes across space. Those ashes coalesced into new stars, new planets. One of those planets became Earth. And on Earth, those atoms arranged themselves into life, into you. You are stardust, literally. And so is everything you've ever touched, the ground beneath your feet, the air in your lungs, the person sleeping next to you. All of it is the remnant of ancient stars. The universe made you, and through you, it looks back at itself. It wonders, it questions, it tries to understand its own existence. That's extraordinary, and it's temporary. You're a brief arrangement of atoms that will one day disperse. The elements that make up your body will return to the earth and eventually to space. They'll become part of something else, a tree, a cloud, a distant star. The universe recycles everything. Nothing is ever truly lost. It just changes form. And if that's true for you, if your atoms will one day become something else, then it's true for the universe too. Even if it reaches heat death, even if it cools into maximum entropy, those atoms, those particles, those bits of matter and energy will still exist. They'll just be spread thin, quiet, still, but not gone. There's comfort in that, if you let yourself feel it. The end isn't annihilation, it's transformation, a rearrangement, a return to simplicity after a long journey through complexity. In Western culture, we often think of death as the opposite of life, the enemy. something to fight, to delay, to fear. But in many Eastern philosophies, death is just another part of the cycle. Day turns to night, summer turns to winter. Life turns to death, and death nourishes new life. It's not a tragedy, it's the rhythm of existence. The universe follows the same rhythm. Birth in the Big Bang, life in the era of stars and galaxies, death in the heat, death or the big rip or the big crunch, and maybe rebirth in a new cycle. But even if there's no rebirth, even if the end is final, the cycle we've already experienced is enough. It happened. It was real. And the fact that it won't last forever doesn't diminish its value. This is the hardest lesson, the one we resist most, that something can be meaningful even if it's temporary, that love is real even if it ends, that life is precious even if it's brief, that the universe is beautiful even if it's dying. We make a mistake when we equate permanence with meaning, when we assume that only eternal things matter, because if that were true, nothing would matter. There are no eternal things. Not really. Even if the universe cycles, even if it's reborn, each cycle is still finite. Each one still ends. And even the multiverse, if it exists, might not be eternal. We don't know. The equations hint at possibilities, but they don't promise forever. So meaning can't come from permanence. It has to come from something else, from experience, from connection, from the fact that right now, in this fleeting moment, you exist, you're conscious, you're aware. You can look up at the stars and feel wonder. You can hold someone's hand and feel warmth. You can listen to a story about the end of the universe and find it strangely comforting. That's meaning, not permanence, presence. The poet Mary Oliver wrote, "Tell me, what is it you plan to do with your one wild and precious life?" She understood. Life is wild, unpredictable, chaotic, and it's precious precisely because it's finite, because you only get one, and the universe is the same. One long, wild, precious journey from beginning to end. And here's the thing, we're lucky to be here now, in the era of stars, in the age when the universe is still warm, still bright, still full of possibility. Future civilizations, if they exist, will look up and see a darker sky, fewer galaxies, less light. They'll live in the twilight of the cosmos, watching the last embers fade. But we're here in the afternoon, when the sun is still high, when there's still time to explore, to discover, to wonder. We're lucky, and we don't always realize it. We take the stars for granted. We assume they'll always be there, but they won't, not forever. One day the last star will flicker out, and the universe will enter a long, dark night that never ends. But that day is trillions of years away. Right now the stars are still shining, galaxies are still forming, life is still evolving. And on this small planet, in this brief moment, you're here, listening, thinking, feeling, and that's a gift, a cosmic gift, because it didn't have to happen. The conditions for life are so specific, so narrow, so improbable, and yet here you are, a temporary arrangement of stardust, conscious enough to contemplate its own temporary nature. That's the paradox. You're insignificant in the grand scheme of things, a speck on a speck in a vast, indifferent cosmos, but you're also miraculous, a local reversal of entropy, a pocket of order in a universe drifting toward disorder. And for as long as you exist, you matter. Not because you'll last forever, but because you're here now. The end of the universe doesn't diminish this. If anything, it amplifies it. Because if the universe is dying, if entropy always wins, if everything eventually fades into silence, then the fact that anything exists at all, stars, planets, life thought, is even more remarkable. It's a rebellion, a defiance, a brief, beautiful moment of complexity in a cosmos that prefers simplicity. And maybe that's the real lesson. Not that endings are sad, but that they make the journey meaningful. Not that impermanence is tragic, but that it's the source of all beauty. Not that the universe is dying, but that it lived, that it gave rise to stars and galaxies and planets and you. And that for a while, it was glorious. So, when you look up at the night sky, when you see the stars scattered across the darkness, remember this. Those stars are temporary. So are you. So is everything. And that's okay. That's more than okay. That's beautiful. Because beauty doesn't need to last forever. It just needs to exist even for a moment. Like a firefly's glow, like a wave breaking on the shore, like a universe burning bright before it fades. Have you ever thought about what you would do if you knew the universe was ending? Not in some distant abstract future, but soon. What would matter to you then? What would you hold on to? What would you let go? The truth is we already know the answer, because the universe is ending, slowly, inevitably. And so are we. Not in the same way, not on the same time scale, but in the same direction. Toward stillness. Toward rest. Toward the quiet that comes after all the noise, and knowing that we still find ways to love, to create, to laugh, to connect. We still look up at the stars and feel something. We still tell stories. We still reach for meaning even though we know it won't last. That's the most beautiful thing of all. Not that we're eternal, but that we choose to care anyway. That we choose to find joy in temporary things. That we choose to love what we'll eventually lose. The universe is dying. And it's beautiful. Not in spite of that, but because of it. And as we near the end of this long, quiet journey through cosmic time, there's one last thing to say. One final note before the silence settles. Let's bring it all home. We've traveled far tonight. Through 13.8 billion years of cosmic history. Through the births of stars and the deaths of galaxies, through heat deaths and big rips and cyclic universes, through endings that feel like beginnings and beginnings that carry endings inside them. And now we've arrived here at the quietest part of the story, the part where we stop running through the timeline and just sit and breathe and let it all settle. The universe is dying. We've said it so many times tonight that maybe the words have lost their weight. But let's feel them one more time. Really feel them. The universe, this vast, ancient, magnificent cosmos that gave birth to everything we know, is slowly, inevitably moving toward its end. Not tomorrow. Not in your lifetime or your great-great-grandchildren's lifetimes, but eventually. Trillions of years from now, the last star will flicker out. The last black hole will evaporate. And what remains will be silence. Perfect, absolute, eternal silence. And you know what? That's okay. It's more than okay. It's exactly as it should be. Because the universe has already done something extraordinary. It started as a point of infinite density, exploded into existence, cooled and expanded, formed the first atoms, ignited the first stars, forged heavy elements in stellar furnaces, scattered those elements across space. In supernova, explosions collapsed them into new stars and planets, and on at least one of those planets, maybe countless others, gave rise to life, to consciousness, to beings capable of looking up at the night sky and asking, why, how, what does it all mean? That's a miracle. Not in the religious sense, though. You're welcome to see it that way. But in the purely physical sense, the conditions had to be perfect. The laws of physics had to be balanced just right. If gravity were slightly stronger, stars would collapse too quickly. If the electromagnetic force were slightly weaker, atoms couldn't form. If the universe expanded too fast, matter would never clump together. If it expanded too slowly, everything would collapse back into itself before stars could form. But somehow, the universe threaded the needle. It found the narrow path between too much and too little. It created a space where complexity could emerge, where hydrogen could fuse into helium-helium, into carbon-carbon, into oxygen, and on up the periodic table until you had all the ingredients for life, for thought, for wonder. And it did this knowing, if the universe can be said to know anything, that it wouldn't last. That entropy would win. That the second law of thermodynamics is relentless and unforgiving. That every organized structure would eventually dissolve back into chaos. But it did it anyway. Doesn't that tell you something? Doesn't that suggest that the journey matters more than the destination? That the experience of existing, of burning, of shining, of creating is valuable even if it's temporary? Think about a song, a beautiful song. It starts, it builds, it reaches a crescendo, and then it ends. And when it ends, the silence that follows isn't sad. It's peaceful, it's right. Because the song was complete. It said what it needed to say. And trying to extend it forever, looping it endlessly, would ruin it. The ending is what gives the song its shape, its meaning. The universe is a song, the longest, grandest, most complex song ever composed. And like all songs, it will end. But before it does, it will have played every note, explored every possibility, created every form of beauty it was capable of. And then when there's nothing left to create, nothing left to burn, nothing left to say, it will rest. And we, you and I, and every human who has ever lived, we're part of that song, a brief melody in the middle, a few notes in a symphony that spans trillions of years. We don't last long. A human life is nothing compared to the age of the universe. But we're here. We're real. We matter. Carl Sagan said something else worth remembering. He said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Every time you look up at the stars, you're not observing something separate from yourself. You're looking at your ancestors, the stars that died billions of years ago, so that you could be here now. Their atoms are your atoms. Their story is your story. And when you die, not today, not anytime soon, but eventually your atoms will return to the universe. They'll become part of the soil, the water, the air. They'll be absorbed by plants, by animals, by future generations. And eventually, billions of years from now, they might find their way back into space, back into a star, back into the cosmic recycling program that's been running since the beginning. You're not separate from the universe. You are the universe. A temporary configuration, a local concentration of matter and energy that became conscious just long enough to look around and say, "This is strange, this is wonderful, I don't understand all of it, but I'm here and that's enough." That's all any of us can do. Show up, pay attention, appreciate what's here while it's still here, and then let go when it's time to let go. The universe is teaching us this lesson in the most profound way possible, by showing us its own ending, by letting us see through mathematics and observation that even the cosmos itself is impermanent, that nothing lasts forever, not stars, not galaxies, not space-time itself. And if the universe can face its ending with grace, without resistance, without fear, just following the laws of physics to their inevitable conclusion, then maybe we can too. This isn't nihilism. It's not despair. It's the opposite. It's acceptance. It's peace. It's the recognition that life is precious because it's brief, that love is meaningful because it's fragile, that the stars are beautiful because they won't shine forever. The Japanese have another concept, wabi-sabi, which celebrates the beauty of imperfection and impermanence. A cracked tea bowl, a weathered piece of wood, a flower starting to wilt. These things are beautiful not despite their flaws and their transience, but because of them. They tell a story. They show the passage of time. They remind us that everything is in flux, and that's okay. The universe is the ultimate expression of wabi-sabi, flawed, imperfect, impermanent, full of asymmetries and irregularities and things that don't quite make sense, but beautiful, so unbelievably beautiful. And you don't need to understand all of it to appreciate it. You don't need to solve the equations or grasp the implications of quantum mechanics or know exactly how dark energy works. You just need to look up, to feel small, to let the vastness wash over you, to remember that you're part of something bigger than yourself, something that started long before you were born and will continue long after you're gone. That's not depressing, that's liberating. Because it means you don't have to carry the weight of the universe on your shoulders. You don't have to figure everything out. You don't have to last forever. You just have to be here now, fully, completely, without holding back. The universe is dying, but it's not dead yet. and neither are you. So, what will you do with the time you have? With this brief flickering moment of consciousness in a cosmos that's mostly dark? Will you spend it worrying about the end, or will you spend it living, loving, creating, connecting, wondering? I hope you choose the latter. I hope you look up at the stars and feel gratitude instead of fear. Gratitude that you're here in this moment when the universe is still young enough to have stars, still warm enough to have life, still strange enough to inspire wonder. Because one day far in the future, long after we're all gone, there will be no one left to look up, no one left to wonder, no one left to tell stories about the end of everything. The universe will be alone with itself, drifting in silence, waiting for nothing, because there will be nothing left to wait for. But that day is not today. Today the stars are still shining, the earth is still spinning, your heart is still beating, and somewhere in the quiet darkness of your room, you're listening to a story about the end of the universe and finding it strangely comforting. That's the miracle. Not that the universe will last forever, but that it gave us this moment, this brief, beautiful, impossible moment where atoms arrange themselves into consciousness and look back at their own origin with wonder. We've walked through the twilight of the cosmos together. We've seen the heat death, the evaporating black holes, the three possible endings. We've imagined cyclic universes and quantum fluctuations and the possibility of something beyond the silence. And through it all, we've discovered something unexpected. The end of the universe isn't something to fear, it's something to honor, to respect, to see as the natural conclusion of a story that began with fire and will end with stillness. And maybe that's the most comforting thought of all, that the universe knows when to rest. That after trillions of years of burning and creating and expanding it, will finally be still, finally at peace, finally home. You don't have to wait trillions of years to find that peace. You can find it now, tonight, by accepting that you're temporary, by releasing the need to last forever, by being fully present in this moment because this moment is all you have, all any of us have. The universe gave you this gift, this brief window of consciousness in an ocean of time. Don't waste it fearing the end. Spend it being here, now, awake, alive. Because the universe is dying, yes, but it's also living, right now, in you, through you, as you. And that's more than enough. The stars will fade, the galaxies will drift apart, the black holes will evaporate, and eventually there will be only silence. But before then, right now in this moment, there's light, there's warmth, there's wonder, and there's you. Thank you for being here. Thank you for listening. Thank you for letting these thoughts settle quietly into your mind as the night deepens around you. Thank you for being curious about the end, brave enough to contemplate it, and wise enough to find peace in it. The universe will end, but so will this night. And that's okay. That's beautiful. Sleep well, dream gently, and know that whatever happens in the distant future, whatever ending the cosmos eventually finds you were here. You existed. You mattered. Good night, little universe. Good night, dear friend. Rest now. We'll meet again soon with another story, another journey through the quiet mysteries of the cosmos. Until then, may your dreams be filled with stars.